Hey folks, so this is an example that sort of encompasses techniques from both section 1.8 and 1.9. So a nice review of all this linear transformation content. And so it says, let T be a function from R3 to R3, and it's defined by the following definition. So you can see I input a vector of length 3, and I get back out some other vector of length 3. And our goal is to show that T is linear, and we want to find the standard matrix. So showing that something is linear is sort of 1.8 material, and then finding the standard matrix, well, that's 1.9. All right. So let's see how to do this. So if I want to show something is linear, so that's our first step. So let's show T is linear. And remember, there's always two ways of doing this. You can either do this two separate pieces, right? The scalar multiplication part and the vector addition part, or you can sort of do it all at once. I'm sort of in the habit of doing it all at once, so I'm going to, continue practice doing that. So just as a reminder, what I want to do is show that this equation can hold. So T of Cu plus dV, here C and D are scalars, U and V are vectors, should equal, well, sort of splitting it all up, C of T of U plus D T of V. Okay, so this is one way to show that a function is linear. Okay, so let me go ahead and highlight this just so we have it handy. All right, so let's go ahead and just work through this and see if we can prove it. So let's I'll be nice to my reader and set up my notation. So U and V are from R3, and then C and D are just scalars. So these are just real numbers. And let's add notation. So we'll say, well, U is the vector U1, U2, U3, and V is the vector V1, V2, V3. Okay, we've seen this idea before. It often is helpful to introduce the actual notation so we can actually compute stuff. Okay, so let's go ahead and start computing. So remember, what I want to do is start on the left-hand side of my desired equation and work my way right. So T of this thing is, okay, it's T of, all right, Cu plus dV. Well, that's pretty complicated, so I should take my time doing this. So it's Cu1 plus dV1, and then Cu2 plus dV2, Cu3 plus dV3. Okay. All right, so what have I done? I've taken the scalar multiplication parts and then the addition and kind of just put it all together. So this is one big vector, right? This is one big vector. And now I'm going to apply my definition. All right, so I have to do this kind of carefully, right? So I have to be looking up here. So my x1, right, my first component is this entire first thing, right? Cu1 plus dV1 and so on. So if I'm going to apply this definition, I have to be very, very careful, very careful. All right, so let's see. So this equals, so what's the first component in this output? The first component is x1, so the first thing, Cu1 plus dV1. Maybe I'm going to like color code a little bit. I think that might be helpful for me personally. So this x1 is this x1. Those are all my x1s. Maybe it's hard to do this on maybe I've just used that color. It's hard to do this on an exam or a quiz, right? But it's good to help us build practice, I think. Color code all the things that are matched. It's too similar. I'll make this one this color. Okay, there's my x3. Okay, so I did that just so I can keep track of where all these things are. So that's going to be plus x2, which is the second component. So that's Cu2 plus dV2. And then my second component is the x3 component. Okay, so that's Cu3 plus dV3. And my last component is -2 times the x1 thing. So that's Cu1 plus dV1. Okay, so I think I did that right. All right. Now you're staring at this, and you might say, oh my gosh, where am I trying to go? Well, remember, there's always this nice strategy of, I know where I'm gonna try to end up. So I could always start working backwards. And I'm almost inclined to start doing that because it's a little bit hard to see exactly what I'm aiming to do here. So I know the final equation or the final expression I'm trying to reach is, okay, this all equals C T of U plus D T of V. And so let me kind of just work backwards just a little bit. So what's this equal to? Well, I'm supposed to get, okay, so C times, what's T of U? Okay, well, I have to kind of redo what I just did. T of just U would be, what's this? U1 plus U2. And then the third thing, so U3, and then minus 2 U1. Okay, plus D times, and same thing, right? So V1 plus V2, and then V3, then minus 2 V1. Okay, great. All right, so can I link the bridge between these two expressions? Well, let's see. It looks like yes. Looks like I have some hope here. The thing I'm noticing is that I can, okay, going back to where I was before, I can sort of just rearrange terms and split up this vector into two vectors, right? Using sort of standard vector addition. So I'm going to put all my u's into one place. So CU1 plus CU2 and CU3. And then distribute the minus 2 here to get minus 2 CU1. So that's all my C stuff in one vector. And I'm going to put all my D stuff in another vector. Well, yeah, okay. I said it a little bit backwards, but oh, it's correct anyway. I sort of want all the C's and the U's in one side and all the D's and the V's in the other, I guess is really what I want to say. So dV1 plus dV2. So I think that first component, I didn't miss anything. And I want dV3 and then minus 2 dV1. Okay. And now, oh, hey, look, this kind of works nicely, right? Notice from this step where we are now to the next step, I just pulled out the C from the first vector and pulled out the D from the second vector. And now I'm pretty convinced that this all works. And so for me, this is a pretty convincing proof. So let's take a step back and make sure we all agree. So starting from T of CU plus DV, plugged in my expressions, calculate, had to do a little bit of manipulation here in the middle, right? Split stuff apart just the right way. And when I pulled out the scalars C and D, the thing I was left with, well, exactly T of U and exactly T of V. So I was able to get from the left to the right, no problem. So this convinces me that T is linear. Wonderful. Okay, so that is done. But now the next thing I need to do is find the standard matrix. So let's go ahead and do that. That's actually a faster step, it turns out. Okay, so I recopied down the function just for convenience. And so how do we find the standard matrix? Well, remember, the idea here is I need to find the image of each of the basis vectors. So in this case, I need to figure out what happens to E1, E2, and E3. Well, let's find out. So T of E1 equals, okay, so let's see. So I'm going to get, I'm plugging this E1 into this equation, or into this, function. So I'm getting 1 plus 0, 0, minus 2. Okay, so that's giving me a 1, 0, minus 2. And then T of E2 is what? So that's 1, 0, 0. Interesting. And then T of E3 is 0, 1, 0, it looks like. Okay, I think I did that right. And so with these three things together, I now know my standard matrix must be, well, stack all these together. So this is 1, 0, minus 2, 1, 0, 0, and 0, 1, 0. Okay. And so that's my standard matrix. Now, I guess as an interesting sort of final exercise, if you're so inclined, you could always ask yourself, well, is this function T, is this map onto? Is it injective? How would you approach those problems? All right. But that's plenty for this. If you have any questions, please let me know. Hope you found this helpful.